All right, after our brief interruption, so we're coming back to corresponding angles. We've kind of defined what these are, and we've noticed which ones in this diagram would be congruent. If I draw the diagram differently, which it will be drawn differently on your homework, this would change, right? Like if I did 1, 2, 3, 4, 1, 2, 3, 4, I'd technically still have all the same things true here, right? But I swapped the position of those two angles.
Would it be like all the odd numbers are congruent to the odd numbers of the even?
So, but that's what I'm trying to say, yeah. So it's not that angle 1 is always congruent to angle 5. It's that in this diagram,
that like
they're
area.
congruent because they're
And
corresponding.
you can kind of just
Does that
tell
make sense?
by looking at it.
Yeah.
Because it's like the same. It's basically like if like the 5, 6, 7, 8 was moved down and to the right, and then it's like the same thing.
Yeah. Now I'm going to introduce one other thing here, which is a lot of times if we're labeling lines, we'll label them with letters. So in this diagram, T, L, and K are lines. And what we can say, right, what we can say about corresponding angles is this only applies if K is parallel to L, which we would write like this. K is parallel to L. I'm going to do a cursive L just because it looks less like a 1. Okay? So this symbol right here means parallel to. So if K is parallel to L, then angle 1 is congruent to angle 5. Angle 2 is congruent to angle 6, etc. The reason I labeled this line T, this type of a line that cuts through other lines is usually called a transversal. Right? So let's take a look at some things we can prove about corresponding angles. Actually, we're going to look at one thing specifically. All right. So I kind of want to point out something before we keep going about geometry in general, which is this might seem a little bit silly, right? Talking about like vertical angles and talking about like corresponding angles. It's like, how often do you see this thing in life? Never, right? But the idea behind geometry and the idea behind proofs is that we have to start really simply in order to build up to things that are more complicated. So what we're going to be building up to is looking at triangles. Eventually, we're going to be building up to proving some different things about triangles, which actually that does have a lot of applications. But we can't prove much about a triangle until we know some basic things about different types of angles. And so that's kind of where we're going, is we're building up some basic theorems and postulates around angles that we can then prove some things true about triangles. Okay? So we're going to prove now something that's called the alternate interior angle theorem. And we're going to do this using only things that we've proved up until now and definitions that I've given you, right? Different things that we know. Okay? But we're going to do a 2-column proof. And the alternate interior angle theorem, what it says, right, is if, we're going to use the same diagram, if K is parallel to L, then angle 2 should be congruent to angle 7. Or and actually, angle 4 is congruent to angle, which one do you think?
No, 5.
So look at the name of this. Alternate means on the other side of the line. Interior means on the inside of the parallel line. So the alternate refers to the transversal. It's on the other side of the transversal. Interior refers to the parallel line that's on the inside. So the alternate interior angle from 2 is 7. The alternate interior angle from 4 is 5. And we can't talk about this with 1, 3, 6, or 8 because those are what's called exterior angles. Okay? So these angles in here are my interior angles. And then these and these are my exterior. So it's just another way of kind of naming and labeling this diagram. Right? We've got interior, exterior, transversals, parallel lines. We still have the thing of vertical angles on here and corresponding angles.
So that means 3 would be exterior?
So like,
So 3,
yeah,
1,
we're gonna,
6, and 8?
and what I challenge you to do as you're doing your homework tonight too, is to think about what else we might be able to prove. Because this is going to be our first theorem. Tomorrow we're going to look at another one, right? Using the same diagram. But there are some other things that we can also prove about the angles on this diagram. Okay? So I challenge you to think about that as we're going through these proofs. But first, let's just prove the alternate interior angle theorem. So if K is parallel to L, can we prove that angle 2 is congruent to angle 7? Let's just prove this part.
Okay.
Yeah, did you have the question?
Oh, couldn't we use the last thing we proved for our homework?
We can use the vertical angle theorem.
Because what we proved last
So
time
let's,
our homework would say
yeah,
that
let's
like,
just talk through it for a second. Okay.
6 and 7 would be equal according to what we did on our homework.
Okay.
And then 2 equals 6, so 2 equals 6 and 6 equals 7. 2 equals 7.
Totally. So 2 and 6 are corresponding angles, right?
Yeah.
So they have to be equal.
Mm-hmm.
6 and 7 are vertical angles, so they also have to be equal. So doesn't that mean that 2 has to be equal to 7?
Yeah.
So now we just need to walk through how would we actually lay that out as a proof. Okay. And I want to start with something that we didn't talk so much about yesterday, but I want to start with the idea of a given. So the given in this case is that K is parallel to L. In most proofs, you're actually going to start with something that's kind of given to you. What that means is it's something that someone has told you to be true. And in this case, we wrote it as an if statement.
Mm-hmm.
So if K is parallel to L, in other words, we're given that K is parallel to L.
Because you're trying to find out what would happen if it is parallel, so
right.
we can figure that out.
And so we know that if these two lines are parallel, then what do we know? Well, we know that the corresponding angles are then congruent, right? So since the lines are parallel, we can now say angle 2 is congruent to angle 6 because of what?
Because of the corresponding angles.
Corresponding angles. Remember, corresponding angles only apply if the lines are parallel. So we have to show this before we can show this.
Okay.
Right? Okay, what else do we want to say? It's actually going to be, I think, important to label these two. So this is step 1, this is step 2. What are we going to do for step 3?
You do angle 6 and 7 are equal.
Yeah.
Angle 6 is congruent to angle 7. Why?
Because they're vertical angles.
Yeah, because we proved the vertical angle theorem. So vertical angle theorem. And just so you know, in geometry, like in high school, your teachers may want you to write things like really in very specific ways here. So you just have to kind of, we're going through more like this year our goal is to go through the logic of proofs a little bit more than it is to get into some of the really specific details that you might end up looking at next year. Okay? So I really just want you to be thinking about this. But like your teacher they might require you to write theorem here, for example. Right?
Oh, okay.
I'm not going to worry too much about stuff like that. Okay. So angle 6 is congruent to angle 7. So then what can we show?
Oh, like that thing where we combine the two?
Yeah.
Yeah, so we actually can't do that yet.
Oh, because it's not fun.
No.
Because
We have something called the transitive property of equality. Which means that, right, if A equals B and B equals C, then A equals C. Why can't I use the transitive property of equality here?
Because it's not actually equal?
Yeah, this doesn't actually say equal. This says congruent.
So
And we haven't proved the transitive property of congruence.
Yeah.
Wait, could we?
Yeah.
Wait, does that mean we could just like put the measure of those two and then make
Yeah.
it equal?
Totally. So we could define this as, okay, so because I know what congruency means, this is just the definition of congruence, right? And then I'm going to use that same definition to show this.
You couldn't skip that step, could you? Like, you couldn't just go straight to the M?
Not really.
Okay.
I mean, we could try to prove that congruency is transitive. Like, we could try to see if that's always true. Like, just if two things are congruent, does that have to be transitive? And then we could just like have a transitive property of congruence. But I don't want to. I think it's important to remember like what congruency means and that congruency is different from equality.
Yeah.
Okay. So the definition of congruence. The other thing that I would put in here is I would write step 2 and 3, because sometimes what happens in a proof is we use something that we showed further up in the proof, right? Like in step 2, I showed that angle 2 is congruent to angle 6.
Mm-hmm.
I didn't use that in step 3, right? So if I'm going to call this, I'm actually going to write it in my justification over here.
Okay.
So if I'm ever calling or using something that I didn't show in the step just before, then I want to actually write which step I got it from. Does that make sense? If I'm just going like, okay, this step and then like this to this, that's fine. Yeah. But if I'm going up here to down here, I want to call that step in my reason. Okay? So now it's equals, so now we can use the transitive property, right? So in step 5, the measure of angle 2 should be equal to the measure of angle 7 because of the transitive property of equality. If 2 equals 6 and 6 equals 7, then 2 must equal 3. I mean, 7. Alright, so transitive. Okay, and that's what I wanted to show, right?
What's that? 2 equals 7. Oh, and then we have to show the other one.
But what did I want to show here? I didn't want to show that the measure of angle 2 equals the measure of angle 7.
Oh, that.
We're being really technical. I want to show that they're congruent.
But then what would you use to? Is it the definition of equality?
The definition of congruence.
Oh. Okay.
And this, right? This gets at something really interesting about proofs, right? Or about properties. We just use this definition in 2 different ways. We used it to show that congruent angles are equal. We also used it to show that equal angles are congruent.
So you like used it both ways?
Yeah. And actually, every theorem that we've learned so far, we could use both ways. Like this theorem, it doesn't just say if K is parallel to L, then angle 2 is congruent to angle 7. It actually also says that if angle 2 is congruent to angle 7, then K is parallel to L.
Oh yeah.
And there's a way that we do this in math, which is kind of weird. I don't actually know the origin of this. But instead of saying if, we actually say IFF. And this means if and only if. And so you're actually going to see this in a lot of proofs. It's not just that if K is parallel to L, then angle 2 is parallel or is congruent to angle 7. It's if and only if.
So if there's any other possibility.
Which means that it can go both ways.
Yeah.
It means that if this is true, this is true. It also means if this is true, this is true. Okay? So that's what this IFF, this if and only if means. It means that the if statement goes both ways. Alright. So this is the corresponding angle theorem. Can anyone think of like a different way we might have proved it?
By using the angle of 4 and the angle of 5.
Okay, so we could have just proved two different angles and then done kind of the
so
same process.
do we have to, if it says that we're trying to prove both 2 and 7 and 4 and 5, does that mean we would technically have to go through the exact same thing but with the other numbers, or is this already sufficient to say that they?
Yeah, this is really sufficient because they're really the same thing. Like if I were to draw this diagram the other way, we would have already proved that.
Mm-hmm.
I'm kind of using like a shortcut here. Like these are alternate interior angles. So technically what we want to do is like define what that means. Like what is an alternate interior angle? Right? And then we would want to make a theorem saying that alternate interior angles are congruent. But I'm kind of skipping that first step. We're not really defining because I kind of think it's obvious in a way. Like alternate interior means that they're on the inside and they're alternate. So these are these are these. Right? So technically what the alternate interior angle theorem should say is that if your lines are parallel, then the alternate interior angles are congruent. But in order to do that, you have to define what an alternate interior angle is first. And we didn't, like I said, I'm kind of like skipping a couple steps. And we're just really going more for the logic of like how do we show something rather than every little minute detail of how we should lay out our definitions and postulates. Like, could you prove this? I'm trying to think if there's another way to prove it. This is how I would have proved it, right? But sometimes there's multiple ways to prove things. Like, could you prove this with showing that things have to be supplementary? Like 2 and 4 are supplementary.
5 and 7 have to be supplementary.
5 and 7. Yeah, I guess that doesn't really help.
Yeah, it doesn't really make sense.
Anyway, it's always good to think. You know, in math we talk about elegance, right? An elegant proof is kind of like the simplest proof that we could think of. And sometimes you'll go through this whole long thing to prove something, and then you'll realize, whoa, I could have proved that in like 5 steps instead of 72, right?
You want a concise proof.
And so, yeah, we want it to be kind of concise in that way. All right. I think that's good.
Wait, Nate, what's a postulate again?